we said that we had gotten the governing differential equations with the boundary conditions for the momentum transport. And we said that we can solve those equations to find the boundary layer thickness, velocity profile, and the drag force and the shear rate, right? And we actually follow the procedure called von Karman integral method. And using this method, we actually we were able to find out the velocity profile up to third order polynomial. And we said that with this approximation, we obtained the velocity profile that depends on y over delta. And we said that the dependency of the Vx with respect to x is actually absorbed in the term delta x. And this actually gives us a picture called similarity stretching that tells us that the Vx over V infinity is a function of y over delta, and it's this dependency doesn't change along the x. So yeah, as you can see in this figure, you can plot y over delta versus Vx over V infinity, and it's the same function for all x's. Okay. Although you just like zoom in and zoom out depending on what the value of the x is, so you can actually get a larger delta for a larger x, but the dependency of the x over V infinity is strict to y over delta. Okay. We said that we can use this to get some quantities which are of engineering interest, right? First, we related the boundary layer thickness to the Reynolds number as a function of x, the Reynolds number with respect to x. And we use this relation to find out the wall shear stress, which is also a function of x. We have seen that the shear stress changes with the position. And we said that using, we said that we can get the skin friction coefficient by using its definition, which is the shear stress, wall shear stress, normalized by the average, what is that, 1/2 rho V infinity square is the average density of the kinetic energy of this stream. And we found that the skin friction coefficient is inversely proportional to the square root of the Reynolds number. And we found numerically the, like with approximation, sorry, not numerically, but with approximation, we found that the proportionality constant. Now we actually said, let us find the drag force now, right? So that's what we're gonna do today. And here, when we say drag force, actually, we're gonna do a similar thing, but the CF, as you can see here, the skin friction coefficient is a function of x. So the friction coefficient is changing along the x direction. But you can calculate using integration the total force acting on the objects, or the total force needed to keep the object at that position. So that's going to be a fun activity to do. Let's say page 3. Oh no, let's not go with this. Let me make another one. So edit, page 3, delete. Let's go here. Okay, good. Now we said, what about the drag force? And let's draw the schematics to just help us understand, right? So imagine you have some geometric shape, but just for the sake of simplicity, let's work with plate geometry, which is going to help us evaluate the integrals in a simpler way. So let's get a shell here. And this thickness is dx, or you can call it delta x. The length of the plate is L. The width of the plate is B. Okay. And I want to calculate how much of force is needed to hold this piece in place. And I'm going to sum over all those forces. So that infinitesimal force, we can call it dF drag, is equal to so what is the drag force in terms of the shear stress? What is the force in terms of shear stress? So you know that the shear stress is equal to force divided by area, right? Area acting on it. So the force is basically the shear stress times area. So you get tau wall, the shear stress at the wall, times the area, which is basically B times dx. Because this much is B, this much is dx, and this area is B times dx. Right? You're doing nothing fancy. You're just calculating the infinitesimal area there. And now, if you integrate, you find out that the FD is equal to sum from 0 to L over x tau W B dx, right? And since this is a flat plate geometry, B does not change with x, so B, you can take it out of the integral, 0 to L, tau W dx, right? And that's equal to B integral from 0 to L. Now tau W, we have found that, right, in the previous class. What was tau W? Let's see. That's 3 mu V infinity over 2 delta. But instead of delta, we can write it in terms of this expression. Okay. This expression. So, oops. You can use this to get the following. 3 mu V infinity divided by 2 delta, but delta is a function of x. Instead of delta, I'm going to write down, what was that? Okay, let me check my notes here. It was square root of 0.139 divided by, let's see, 3. We estimated that, but we can re-estimate, it doesn't matter, times square root of V infinity x over, actually it's in the denominator, infinity over x nu, right? Okay. Dx. So that should be the tau wall. And if you proceed forward, you can take these entire thing out of the parentheses. And also this term is a constant. So you can have B times square root of, 3 times 0.139. I just combined this with this. to make it the 3 squared divided by 3. Divided by 2. Mu in parentheses v infinity cubed divided by nu times integral x to the power -1/2 it's 1 over square root of x, right? From 0 to L dx. So this is a really good practice for your calculus skills, right? And what do we have here? Okay, so this one, it's going to be like x, if it's x to n, remember that it's x to n plus 1 over n plus 1. So it's going to be x to 1 over 2 over 1 over 2, right? But the 1 over 2, you can write it as like 1 over 1 over 2 is just 2. So it's this, and you can cancel this 2 and this 2. So you get b times square root of three mu. Let's take the mu. Let's keep the mu there. V infinity cubed divided by nu. And this one is basically, if you plug in L here, you get L to the power 1 over 2, and if you plug in 0, you get 0. So that's this term minus 0. So and you can take it inside the square root because it's already within the square root, right? So that's it. So that's the friction force, right? So let's box it. Acting on a plate with a length of L, the width of B. Okay. We can also calculate what's called as a drag coefficient. Which is CD, which you may remember from your fluid mechanics course. That's similar to the skin friction coefficient, but instead of the tau, you have the drag force in the numerator, drag force divided by 1/2 rho V infinity squared, but this time we do not normalize only with the kinetic energy density, but we multiply with B and L, the total area of the plate. It's basically, this is more like an average, right? As you know, drag coefficient. Similar to CF, but you're basically taking like an average approach, like you're taking like average shear stress FT divided by the entire BL instead of infinitesimal tau W. Okay, and we can estimate it. Let's write down B square root of 3 times 0.1, oops, 39 mu square root of V infinity cube L over mu divided by 1/2 rho V infinity squared B times L. These cancel. And you get square root of times 3, 12 times 1 through 9. Mu over rho, this is new, right? So you can take it within the square root. That's going to be V infinity cube L. Instead of mu over rho, we have nu outside, but you can take it inside as nu squared, and it's gonna cancel with this nu, and you have L squared coming from, oops, you have L squared coming from this term, right? And you have the fourth power of this, V infinity to the power fourth. And after the cancellations, you cancel one of the L's, you cancel one of the nus, you cancel 3 of the V infinities, correct? Yep. V infinity, so you get the following. Square root of 12 times 0.139, square root of 1 over, let's rearrange it, L V infinity over nu. This is the Reynolds number, right? Reynolds number L. So we found that it's 12 times 0.139 Reynolds number L to the power -1/2, right? And let's write down, probably you're saying, oh, why are we not just estimating this? 1.292 Reynolds number L -1/2. So we get the drag coefficient. Isn't that cool? That now you can estimate the drag coefficient if you know the flow conditions. If you know, for example, if you know that the air is actually flowing around an object, like around your car, and if you know the speed of your car and the air outside is stagnant, you can calculate the Reynolds number that's flowing around your car with respect to your car. And from that, you can calculate the drag coefficient. And from that, if you know the area of your car, you can calculate the total force acting on your car by the air, like the aerodynamic force. So this is like a complete. This is completely important in engineering applications. Okay, so you can solve many problems like particles sedimenting in water, like the drag force around objects, like for example airplanes or cars, and the force acting on a plate, which is basically surrounded by a stream of water, for example. So you can calculate this CD using this approximation. And is this formula valid for high Reynolds or low Reynolds? What do you think? What was the main assumption we made in all these derivations? Any idea? Any idea?
When delta is much less than L,
Exactly. So when delta is much less than L, which means Reynolds number is large or small?
Reynolds number is large, I think.
Reynolds number is large, exactly. So let's go back to that derivation. Oh, what happened to this? Yeah, if you have a look at this, for delta is so small, Reynolds numbers should be so large, or this one that we had derived, or numerically we had actually derived after we solved these equations, right? Yeah, there you go. So when delta is so small, Reynolds number must be large because it's inversely proportional to the square root of Reynolds number. So we can say for high Reynolds number flows, not for laminar ones. Okay. Good. So far, so good. So now what are we going to do? We learned like a lot about the boundary layer theory for momentum transport. Now, let's actually go ahead and do it for the heat transfer, right? Let's say boundary layer theory for heat transfer. Okay. Okay, so what are we going to learn? We're going to learn about the energy equation. We're going to derive this from shell balance. Okay, so this is the energy equation for boundary layer thickness. And we're going to apply it thermal to find the thermal boundary layer. Okay, so let's say first the derivation of the energy equation. Now, analogous to the what's called as a Navier-Stokes equation. For momentum transfer, we can derive a thermal energy equation for heat transfer. Okay, and actually forgot about which chapter we are actually dealing with, right? I forgot about to tell you. Okay. So this is chapter 19.4, not the derivation, by the way. We will this basically this part, chapter 19.4 and 19.6 in textbook mainly, but take it with a grain of salt, meaning that there are things that I mention extra, and there are things the book actually mentions extra. So some of the things might be, some of the things that I'm discussing here might be missing in the book. Okay. So what about this thermal energy equation for heat transfer? Check WELT textbook, chapter 16. Okay, or in BSL for Stuart Lightfoot. That's the second one, second textbook. It's not the textbook, sorry, it's the recommended book. Chapter 11 for those who are interested. Let me quickly check chapter 16, the book. Yeah. It's the differential energy equation. It's, let's see, yep, 16.1. Okay. So it's basically, let me write it exactly from there, and then we are going to derive it for our particular case. Okay. Del dot K del T plus fancy R dot. In the book, it uses the notation Q dot, but I like change it as fancy R dot because that's the notation I'm using. I use fancy R dot for the heat generation plus phi is equal to rho Cp dt over dt. Okay. Well, actually, for the incompressible fluids, Cp is almost equal to Cv, but for the compressible ones, so incompressible ones, they can be equal to each other, but for the compressible ones, not necessarily. So let's use the notation Cv instead, the heat capacity at constant volume. This is the energy equation. It's the equation 16.13 from the textbook. But this is a general equation where you have it for not necessarily for flow around a plate or a spherical object, but the general one. But we are going to derive like a special form of this for incompressible fluids in 2 dimensions just for the sake of solving the boundary layer equations. Okay. And this phi is the viscous dissipation. Okay. It corresponds to the fact that if the fluid is highly viscous, there is going to be heat generation just because of the layers of the streamlines of the fluid actually flowing at different velocities from the adjacent streamlines, meaning that it's like if you get like two blocks and move one on top of the other one, and if you just like try to like push them each other and just squeeze them and slide one on over the other, you're going to see that the interface is going to heat up. Or maybe if you just rub your hands are going to heat up. It's the similar effect. Viscous dissipation corresponds to the heat generation because of the streamlines moving one on top of the other might generate heat. Okay. Good. And R dot is like any type of heat generation. So let's derive this equation. Derive our own energy equation for finding using shell balance. So we're going to use a similar approach as in the book, but I'm going to do the simplifications during the derivations instead of finding the overall equation and then simplifying it. So that's another approach. You can find this equation and then simplify it by saying, for example, the k is constant, you take it out. It's two-dimensional, you only like consider, for example, derivative with respect to x and y instead of z's and so on. So you can simplify this equation, but instead, I'm going to actually start from the beginning and like step-by-step simplify things while I drive it. So this is a good exercise for doing a shell balance. Okay. Imagine that we have like a plate, right? And fluid flowing around the plate like this. And imagine you take a shell. Oops. With the dimensions delta x, delta y, delta z. Okay. And then imagine that the streamlines are going along this direction. They're entering and exiting your shell. Okay, you can think of it like a general case where you have some fluid stream, and we're going to take into account how much heat is being added to the system, how much heat is exiting the system, and so on. Okay, so okay, so let's do shell balance. Rate of heat in let's say thermal energy in. Minus rate of thermal energy out plus generation rate of thermal energy generation is equal to rate of thermal energy accumulation. First of all, this is very similar to what we have done so far, to the shell, like very similar to the shell balances that we have done so far. The only difference is the following. We had taken care of only the conduction in which our object was not moving. But in this case, we are not doing a shell balance on a solid object. We're doing a shell balance on a fluid stream, meaning that I do not have only the conductive terms, but I also have the convective terms. Sorry, not the convective, but it's called, forgot the name of the term. But there's going to be heat transfer just because of the motion of the stream. The stream itself getting into the shell and coming out of the shell. It's unlike the conduction we have actually done for the solid objects, right? Yeah, that's advective flow. So that's advective heat transfer that we are taking care of right now. Let's assume that this is steady state and no accumulation. And let's assume that there is no thermal energy generation. And we are also neglecting here the viscous dissipations and so on. So let's assume that the viscosity is not like very large, so that we can neglect the energy generated from the viscous dissipation, or there's no other like chemical reactions happening that generates heat. Okay, I only have thermal energy in and out, but I have like 4 different terms for each, because thermal energy can get in with conduction or advection, and also it can get in along the x direction, and it can get along the y direction. So let's say it has 2 terms due to conduction and due to advection. Similarly, for the thermal energy out, we have the same things. Okay. So rate of thermal energy in due to conduction is, you can call it as Q conduction. Yeah, let's call it Q along the x direction, right? But you multiply it with the surface area, right? The one coming along the x direction actually meets the surface area of delta z times delta y. Correct? And you calculate it at x plus conduction along the y direction, qy, delta z delta x this time, because the y stream is meeting an area of delta x times delta z. It's penetrating into that area at y. That's the thermal energy in due to conduction along the x and y axis. Now let's add the convective term, the advective term. The advective term means the transfer just because you're moving the object from one place to another. So it's like moving your like hot cup of tea to one place, from one place to another. You're actually having an energy transfer instead of you're holding your cup and the heat is just dissipating with conduction. Okay, so now just because the fluid is moving, right? And you can calculate it using the mCp delta T, right? M times Cp times delta T is the energy that is actually transported from one place to another, but we're going to play with this a little bit. Now, per unit time, mass is just going to be like the mass entering per unit time. Let's call it dm over dt, right? And but it's the mass flow rate, and you can find out the mass flow rate by multiplying the rho, the density, with the volumetric flow rate, right? V dot. But the volumetric flow rate is nothing but the velocity times the area. Velocity along the x direction times velocity times the area. It means is delta y delta z. Okay, any question about this term? So this tells you that how much of energy is entering the phase, which is delta z delta y. So basically, if you multiply the velocity with this area, you find out the volumetric flow rate. And if you multiply it with the rho, then you get the mass flow rate. Mass flow rate into the delta y, delta z phase of the shell, right? Cp delta T, let's talk about basically absolute energies. Instead of delta T, let's call it T, okay? Because later we are going to see that it's, you don't need to, or you can write T minus T reference. But since we're going to take derivatives later, so you're going to see that it's, yeah, you're going to see that it's just going to vanish. So you can just simplify it and have T here. That's along the x direction, plus rho, and this is at x, rho Vy delta x delta z Cpt long z at y, sorry. And now you also have the out terms minus the same out terms. Let me write it here. Minus the same terms, qx delta z delta y x plus delta x. I don't want to rewrite them. So here what I'm going to do is I'm going to use a shorthand notation and say same expressions evaluated at x plus delta x or y plus delta y, okay, is equal to 0 from our equation. And then divide. Now let's divide as we did before. Divide all terms by delta x, delta y, delta z. Okay, and then you're going to see that, for example, in the first term, these two cancel, and you're going to have like, oops, you're going to have like a delta x term in the denominator. For this one, these two cancel and you're going to have delta y in the denominator, right? For this one, again, you're going to have delta x and so on. Okay? And goes on like this. And if you combine the x term with the x plus delta x term here, you basically have nothing but the derivative of the qx, right? And take limit as delta x goes to infinity, 0, and delta y goes to 0. And we get minus d over dx, it's partial derivative, del over del x, qx, minus del over del y, qy, plus, or minus again, del over del x, rho, bx, cp, t, minus del over del y, rho, vy, cp, t is equal to 0. So we got quite a neat equation, right? And assume constant k, rho, and cp, we get and also, and using Fourier's law, we get the following. So this term becomes minus k, so that's plus k, del squared t over del x squared, plus del squared t over del y squared, it's this term, and I took it to common k parenthesis, minus rho cp del over del x vxt plus del over del y vyt is equal to 0. Right? Let's do more simplifications. Now, let's focus on this term. This term is, if you use the product rule, you get t del vx over del x plus vx del t over del x, right? Plus t del vy over del y plus vy del t over del y. But if you can appreciate this term, is t times del vx over del x plus del vy over del y. And do we know what this is? From continuity equation, this thing must be 0 from continuity equation for incompressible fluids. And then we get 0 here, so you can simplify this as this plus this. Okay. Okay. So we got, after simplifications, we get k, and let's divide everything by rho CP as well. K over rho CP del squared T over del X squared plus del squared T over del Y squared is equal to, I have Vx del Vx, sorry, del T over del X plus Vy del T over del Y. Okay, so we got our equation. So this is our heat equation. You can actually get exactly the same equation if you had actually start from this and simplify by, for example, neglecting the R dot term, assuming K is constant. Instead of del's, you write down the Cartesian coordinate representation of the gradients, and so on. Okay. And instead of K over rho Cp here, you can say it's the thermal diffusivity, right? It's alpha times del squared T over del X squared plus del squared T over del Y squared is equal to Vx del T over del X plus Vy del T over del Y. So let me box this one instead.